at this arrive with these equations. So in order to drive equation 2.a, we have considered this equation and we are going to drive it. We know this by, wait a second. So we considered this equation 2.4 and yeah. So by considering equation 2.4, what we do is that first we derivate with respect to x and then we derivate it with respect to y. So in the end we get this result, but this result is actually equal to so we can also get this result if we derivate the, I mean, if you see, if we consider it, and if we can actually come up with this result. Similarly, we can, if we derivate y 3 times, we can 2 times, we can come up with this result. So we just put this value here in here and we get this final result. So nothing to explain here. You can say it's just simplification. Now if we start with this condition, okay. All right. So this identity, what they have done is that they have taken these 4 identities and they put in this equation and they get this result. Okay. And so what they have done actually is that they derive these 4 identities individually by differentiating them, beginning from this, using this and this, okay, as well as this. So let us see if you can come up with just one, the rest you can do easily. So we have d cube u upon dx dy dz. So I guess if let us assume if I derivate it 3 times, okay, so du dx dy dz, okay, so and here it will also be, no, wait a second, so the x is already here, so I just have to derivate with respect to y and with respect to z, okay. Yeah, and this is the square, sorry, this is not cube, this is square. So I can actually, if I double derivate this with respect to yz, I can actually get this expression right here. So let us drive this also, okay. So it says that xy will be dx and dz. So if I move on here, so if I derivate it with respect to dx and dz, if I'm not wrong, wait a second, so we have dx and dz. All right, so we have dx and dz. So let's see, this will be dv square dx square and dz, and this will be equal to, I guess, du square dx dy and dz, okay. So this will be the required expression. So okay, and if I see, I think I've guessed it right, wait a second, oh yes, so I've got this expression. Similarly, you will going to drive these 3 expressions as well, and if you put it in this expression, you will going to come up with the first identity, which is here, okay. So this is how these 6 identities are derived in order to see if the system is actually compatible or not, okay. So moving on, now what we actually have is that we actually have a displacement field, example of a displacement field computed from a strain field. because so what we have is that we have a shaft in this example, and the shaft is undergoing a strain wzx, which is equals to minus ay, and second strain is yz, which is equal to ax. ठीक है, and a is actually the क्या कहते हैं, a is actually the radius of the shaft. So a is actually the radius of the shaft which is loaded, and the shear strain which is produced is given to you by minus ay and ax, and I guess the normal stresses are equal to 0 and one shear strain is equal to 0. ठीक है. Now if you can next substitute equation a in equation 2.4. so this is the equation a. ठीक है, and equation 2.4 is this equation. This equation is the 2.4. so we had this equals to 0. Yes, so 0. So u actually becomes the function of y and z. Similarly, v tends to 0, w tends to 0. ठीक है, so u becomes the function of y and z, g becomes the function of x and z, because there is only x. So since there is nothing in the x direction, so u will be the function of y and z. So and here there is no strain in the y direction, so v will become the function of g, x and z, and similarly x and y. Now we also have this tends to 0. So if this tends to 0, it becomes u becomes the function of f, y, z, and v becomes the function of g, x, z. ठीक है, so if this both equals to 0, I can move one expression from left to right, and I'm going to get this expression. ठीक है, where both of them are function of z. ठीक है, now what I'm going to do is that if I integrate, so what basically happening is here is that the equations is coming out to be like this. So d f yz upon y is equal to function fz, and this is also equal individually to function fz. ठीक है, so what I have done is that I have integrated them separately. So when I integrate क्या कहते हैं, d f z fz dy, and I integrate it. ठीक है, so what I get is this. Similarly, if I integrate this g function, I get this. ठीक है, this is corresponds to u and this is corresponds to v. ठीक है, now wait a second. Alright, so where was I? Okay, so we have the function expressed as fz in terms of u and gz in terms of v. Now this is important as we will going to use these values to determine future variables. So anyways, so it says that recall that sigma gamma yz equals this. ठीक है, and gamma yz is actually equal to this. ठीक है, so the ax is actually equals to dava of w upon dava y, and w equals hxy, and v equals this part. ठीक है, so as you can see, this is what we have gotten. ठीक है, so this is in place of gamma xy, gamma yz. ठीक है, So after forming this equation, what we will going to do is that it says that the equation E can be satisfied if and only if both right hand terms are a function of x alone. So we can see this, we can see here that the h is function of x and y, but it can only work if it's the function of x. Okay, because we have, I guess, x over here. So dou of h x upon dou y becomes the function of x, and tfz upon dz becomes c3. Okay, so this becomes c3. Okay, so it becomes hx minus c3x, so h becomes a plus c3x. Now integrating this equation f, uh, applying the integration, we are going to get fz c3z plus c4, and putting fz in, I guess, in equation h, substituting, which is d here, right here. So we are going to substitute this fz in this equation, and we are going to end up with this v equals, okay, we're going to substitute here and here as well. So we get this equation of u and v. Okay, now by equation b, f and g, we have w equals hxy, and hxy is actually equals to hx dy. Okay, so applying the integration, we end up with this. Okay, so it's just simplification, there is nothing to explain in this scenario. So now we're going to move towards the zxy. So the zxy equals w upon dou x plus dou u upon dou z, putting the values of w and u from the above results. So w equals w, where is w? So w equals this, and u equals u, where is u? All right, this is u. Okay, if I'm not wrong. Okay, applying the derivative, we will going to get this. Okay, so c3 equals minus a. So substituting equation k in equation I and j, we're going to get this, and w equals c5. So now it says that the constants, all these constants are when the strains is actually produced. Wait a second. Okay, these constants have nothing to do with the strain produced in the shaft by the application of force. So since they actually have no value in contributing to the strain, we can actually neglect all these c's, and we can eventually arrive at these expressions. Okay, these expressions actually states how strain will going to affect upon the application of stress on a shaft. Okay, so this was our objective. So now we are going to come to an important concept, which is the volume dilation. So the volume dilation is a concept in which we tend to see the change in volume, and if it is related to the coordinate system which is in which it is actually present. Okay, so consider any cube that has sides a1, a2 and a3. Okay, but after application of some stress, it becomes a 1 star, a 2 star and a 3 star. Okay, so if I want to find out the value of a I star, it will be this. Similarly for a2 and for a3. I guess this should no longer be unfamiliar to you, because we have actually seen this formula, I guess, wait a second. Okay, so we have seen this formula. Wait a second. So yeah, this is the formula. Okay, so we have used this formula and convert it according to our condition. Okay, so I have actually have this formula, and I'm still, what I'm going to do is that I'm going to just plug in the values in this formula as I've done here, and I will going to take common a1, a2, a3, and will going to just cancel it with the denominator. Okay, so if I tend to multiply these three terms with each other, I'm going to get higher products of these e's, which I guess if their products can be neglected, the higher powers can be neglected, and I'll be only left with solution e1, e2, and e3. Okay. Now the thing is that if you can see here, these values are actually strains, or you can, and this is actually equal to j1, which is the invariant of strain. So but if you can see, d, or the volume dilation, is not uh, dependent on either u, v, or w. Okay, so we can see here that it is independent of the coordinate system in which it is operating. Okay, so volume dilation does not depend upon the coordinate system. It is totally independent of it and depends upon the material only. So this is the concept of volume dilation. Thank you. Alright, so now we are going to study the stress and strain relation. Uh, in order to do that, we have formed some equations which you can see on your screen, which is sigma x, sigma y, and sigma z, tau xy, tau yz, and tau zx. And we have formed a linear relationship between the stress and the corresponding strain in each axis, and this relation is between the stress and the strain, normal strain and the shear strain. So there are total, I guess, if I'm not wrong, these constants are 36. Okay, but if we have certain assumptions, and if we apply some strain energy considerations which are beyond the scope of this text as per your textbook, we can reduce this 36 into 36 constants. These constants are basically the elastic constants, which depends upon the property of the material and not the coordinate system that is used. Okay, but with further simplification we can reduce this constant into just two fixed constants, which is sigma and tau. Sorry. We can reduce these these constants into just two constants, which I guess it's Lami's constant and the invariance. Okay, so the thing is that without showing that how this was done, they just simply reduces these equations into here, this one. Anyways, and what he has also done is that the 2.13 was converted into the function of stress as follows, as you can see here. And now what they have done is that they have considered a two-dimensional case of shear stress, in which there is only shear stress and all normal stresses are zero, and two shear stresses are also zero, and they have taken this and converted into this. So it's just a different arrangement, and nothing special is being done. But after but here in this condition, what they have done is that they have considered a special case of stress, in which a special case of uniaxial stress, where stress is just applied in on one axis, which is the normal stress. So in this case, the normal stress is sigma xx, and all other stresses are 0. And 2.14, this equation is reduces into this. So if I write this will be tends to 0, this will be 10 to 0, and this will be 0, this will be 0, and this will all tends to be 0. So this will be equal to this, and this will be equal to this part, and this will be equal to this part, minus sigma sigma z कैंसिल होगा. ठीक है. So you are going to be left with the wait a second, where was I? Alright, so I think I missed that, but you can actually see that. Okay, here it is. Okay, so we end up with these equation. Now what I have done is that I have simply we actually know this from our from our knowledge, and I will going to simply equate this with this one and this with this one, and I will going to get this result. Okay, and also the Poisson ratio is also equal to this. Now I'm going to consider another special case in which all normal stresses is equal to the hydrostatic stress and shear stress is equal to 0. Now in this condition, if I put this plug these values into equation 2.3, which is 2.13, if I plug those values in these equation, I will going to get this. And if I do some rearrangements, I'm going to get in a certain situation like this, where I equate this as k except for the minus sign, and I get this equation in this form. Okay. Now I'm going to put equation 2.5b and 2.5c into equation 2.13 and 2.14. So 2.13, I guess, is this equation. So where is 2.15 b and c? So 2.15 b and c, I'm going to substitute these values in equation 2.13. So I guess it's 2.13 and 2.14. Okay, so I have done this work for sigma xx and this one, and I've done this in the next slide. If you can see here, I have taken these and put it here, and by simplification I get this. Similarly, I did this for gamma xy, and finally got this equation. Okay, so I've got this value of u from table 2.1. You can see I've just put it and got this result. Okay, so, and this equation is just nothing but converting strain into stress. So if you convert strain into stress, and with a little bit of further substitution, you will going to get this equation. I recommend you to not to just simplify it, and just if you can remember it will be better. However, if you want to go the long way, you can. But if this comes up in an exam, and if you just write it that if this equation turns to this equation, I will going to accept it. Okay. Alright. Strain transformation equation and stress strain relation for two-dimensional state of stress. So we actually, wait a second. Alright, Now I'm going to simplify equation 2 point I guess it's 6, in which we have strains in x dash dash y dash and z dash z dash. So we are considering a case in which I orient my axis in such a way that z coincides with the z dash. In such a situation, my EZZ will be equal to E z dash, and sigma zx will going to tends to 0, and sigma gamma yz will be also be 0. And I'm also going to generalize the angle between x and x bar as simply theta. So if I use all of these conditions, and if I put in equation 2.6, 2.6 is this equation. Let me get checked. 2.6, yes, this equation is 2.6. Okay, so this will be theta, this will be theta, and this will be okay, this all these angles will be theta, and this will be tends to 0. So I'm going to end up with this equation. And sigma zz will be equal to Ez, and gamma yz z dash and gamma z dash x dash will also be equal to 0. Now another thing I'm going to do is that I'm also going to assume in a two-dimensional state of stress, from three-dimensional state of stress I'm going to two-dimensional state of stress, and the dimension which I'm neglecting is the dimension z. Hence the normal stress and the shear stress along the z will be equal to 0. And if I put that is in equation 2.16, the 2.16 is this equation. If I put z as 0 and tau yz 0 and tau zx 0, I'm going to just simplify it. So yz equals to this will be 0, this will be 0, will not going to have this, and I will not going to have this, and sigma yz equals to 0. So I will be just left with this expression, and this will be 0, this will be 0. Okay, so the equation which I'll going to get in the end are these equations. Okay. Alright, now moving on, if in a similar manner I consider the same conditions but I put it in equation 2.17. So 2.17 are these equations. If I put that, I'm going to end up with these equations for normal stress and shear stress. Okay, so that's all for this derivation. And yes, in the end, one additional relationship relates to sigma zz to be measured, strain this and this in experimentals obtained from equation 2.17 by substituting gamma zz equals to 0. So this is nothing but if I put sigma zz equals to 0 here, I will going to get expression for this. Okay, so that's all for this lecture. This is not there is nothing much to explain here except for the fact that we considered z going from z dash to z, and considering normal stress and shear stress known that axes to be 0, and we just use that condition and put the values in different equations to get these results. So this is all for क्या कहते हैं This is all for chapter 2, and we're going to see you in the next chapter. So all right, after this video I'm going to solve the numericals. ठीक है, so see you after that. Thank you.